On the first problem, to find the extreme values, global extrema of this function over this rectangle. We'll first find the interior critical points by setting both partial derivatives to 0. And this entailed df dx was 2x minus 2, and df dy was 2y minus 4. So this one says that x equals 1, and this one says that y 2 and y minus 4, that y equals 2. And so there's only one critical point. You have to satisfy both these. It's at 1, 2. That's the only, and it's interior. Any exterior critical points you throw out. I can't give a maximum and a reason or anything. So there's one interior critical point. Then you have to check the boundaries. I drew this picture because when it's segmented like this, you can't just write a nice function for the boundaries. It's easiest just to call these sides. I call them C1 here, C2 here, C3 here, and C4 here. And I just checked along each straight line boundary broke, and I said the boundary C is the union of these, right? So what I can do is find for a one-dimensional problem, what's the maximum value it takes on this boundary, what's the maximum on this one, what's the maximum on this one, maximum on this one, same for the minimum. And then check the corners where they meet. Maybe the maximum's there in the one-dimensional problem. So that's calculus 1. So the boundary, for instance, maybe we won't do all this. We'll just say along C1, you get x. If I make a parametric equation for it, x equals t, y equals 0, gives parametric equations for this boundary where you let t go from 0 to 2. All right, so that sweeps out the lower boundary. And now along that boundary, you have f of x, y, with x and y each a function of t, is f of, well, x is t, and y is 0. So you take f of t 0, then you get t squared plus 0 minus 2t minus 4y is t squared minus 2t. And you want to find what's the maximum and minimum that takes over the interval t from 0 to 2. Calculus 1, right? So if you set the derivative of f prime of t equal to 0, f thought of as a function of t, 3 the intermediate variables x and y, is equal to 2t minus 2, tells you that t equals 1 is the interior critical point, and then you have to check the endpoints separately, right? If you want to maximize function of one variable over an interval, or the continuous function of one variable over the interval, you find all the critical points, find the endpoints, and plug them all in, and the maximum occurs at one of them, and the minimum occurs at one of them. Calculus 1. So I have t equals 1, and so I'm going to check, that tells me I'm going to check the point at t equals 1, which is x equals 1, y equals 0. I have to check that point. Maybe the maximum along that boundary is there. But you do that along all the boundaries. Let's see, another good one to check. Maybe this is the only one I need to check. Let's just say we do that along the other three boundaries too, so it don't take too much time. But like I said, I'll put this all out on the web. I wish we could do it here in class. This is one of the drawbacks to doing this online. So you check along each boundary, and what you find out by plugging them all in, you plug in the interior critical point 1, 2. You plug in the any critical points you find along the boundary, these one-dimensional problems, 1, 0. And there's some other ones. Let's see, there's also 1, 3. And 2, 2. These are along the boundary. And then you plug in the corners where the boundaries meet. Those are the endpoints of these one-dimensional problems. 0, 0. 2, 0. 0, 3, 2, 3. And the largest is the absolute maximum, the smallest is the absolute min. The largest by plugging in is the maximum f of 0, 0, and 2, 0. Both gave a value of 0. That's the largest this function could be over that whole thing. So by plugging in all these points, the largest value you ever get is 0, and it occurs at these 2 points. So this is the maximum, and it's at both of these 2 points, 0, 0, and 2. The smallest is the absolute minimum. That occurs at your interior critical point, 1, 2. Came out to be -5, as I recall. So -5, the z value, smallest z coordinate is the minimum, and it occurs at the point 1, 2. Well, I won't run into details. Like I said, I'll put this up online. If you're here tonight, I'll give you a Xerox if you prefer to. Any questions at number 1? I left out a bunch of details. It's longer than that, but it's just a matter of doing the same thing on all boundaries and yeah, plugging in all the points.
I mean, you do still get to do double integration, right?
No, what I asked you to do was find the global maxima and minima. So if you did the wrong problem, I couldn't give you credit, yeah. But the object then was to find both partial derivatives, set them to 0 to find the interior critical points, parameterize the boundaries, and make one-dimensional problems that you find the max and min of. Plug them all in, see which is biggest, which is smallest. So it's kind of similar to calculus 1, where you're maximizing or minimizing a function of one variable on an interval. You plugged in the endpoints. You plugged in any critical points, and whichever gave you the largest y value was the max, whichever gave you the smallest y value was the min. So there's the min, y value, and max. Except now we have a function of 2 variables that occurs at the boundary of the region on which it's defined, just like this one did, or in an interior critical point, just like this one did. So it's same kind of thinking. I think that really helps you to remember it. Here's number 2. I asked you to evaluate the double integral. I think most of you did really well on this. Of xy dA over region R, where R was a rectangle. By Fubini's theorem, I said do it. R is the rectangle in set builder notation. Set of all xy. R means such that x is between 0 and 4. Y is between 0 and 2. Similar rectangle, the last one is different limits. What that means is that you, by Fubini's theorem, you can evaluate an integral over a rectangle, he says, by integrating x and y between the two ending values. In either order, doesn't matter. I put x on the outside, y on the inside. The integrand, in this case x and y. There's multiple ways to do this, and a lot of you did this perfectly by doing the inside integral and then integrating the outside integral. Since you can do this in this case, I like breaking it up, right? Integral over y, x is considered a constant. You can pull the x out of here, right? Into this part, since it's a constant with respect to the inner integral. So you can rewrite this as integral from 0 to 4 of x dx, and then you pull the dx right through. Integral 0 to 2, what's left, y dy. These are calculus 1 problems, right? And when you calculate those, you get 16. And I'll leave out the details. Most people did pretty well on that one, I think. Stop me if you have questions, though. Okay, here's number 3. Suppose I gave you this double integral here, 0 to 2 2y, y squared of some integrand f of xy, dy dx. Rewrite as an iterated integral in the opposite order. How do I rewrite that in the opposite order? Well, the hint is there, whenever you get this thing to switch the order, and sometimes switching order is important. Sometimes you get one that's hard to integrate in this order. If you write in the other order, sometimes it's easier. All right, so it's actually an important technique from that point of view. What you always do, pretty much always, not every time, but almost always, is you draw the region. You say, well, this, since x is on the outside, y is the inside. Oops, wait a minute. It says dx dy. I wrote it wrong. Dx dy. X, since dy is on the outside, the x is on the inside. You're letting x go between the two curves. X equals 2y. X equals 2y. Like this. When x equals 2, y equals 1, for instance, gives you a point. But it's a line, right? You can put this in the form y equals mx plus b or ax plus by equals c, general form for a line. And it has that point and this point, for instance, so I could draw that pretty easily. There's the one line. And then the other boundary line is x equals y squared. Well, that's just a parabola. And it goes like this. And now you observe all the region between them is this little slice right here. Drawing is really important in redoing the order here. Now I want to switch it to the other order. What I do is I say, as this is, it's a type 2 region, the book calls it, where y goes between c equals 0 and d equals 1. And x goes between a curve x equals one function of y and x equals another function of y. So if I want to rewrite this as a type 1 integral, then I choose the x endpoints. These intersect at this region begins at x equals 0 and x equals 2. The outside limits are always this is 2, this is 4. This one went up to 2, sorry. And this one went over to 4. The point I plotted should have been here, 2, 1. Anyway, they intersect out here. If you set these two equal, you find out this is the intersection point 4, 2. So now I let x go between constant endpoints. The curve, the region starts at x equals 0 and ends at x equals 4. So these are always constant endpoints on the outside. On the inside, since I'm doing a type 1 region now, I go from the bottom curve up to the top curve. I have to put down here the bottom curve, which is actually the line x equals 2y. So I put 2y at the bottom. And I put this one I have to rewrite. Oops, x equals 2y. Yeah. I want to rewrite as equivalently as y equals 1/2 x. And now y is going to go from 1/2 x, the bottom curve, to the top curve. I need to rewrite this one, y is a function of x, y equals square root x. It's x equals y squared. So the top function is square root x, and the bottom function is 1/2 x. One of the biggest mistakes was putting these in the wrong order. You want to go from the bottom function to the top function. If you get it backwards, you'll just change it by a minus sign.
So I
Yeah.
got that
Yeah,
on
that's
paper, but it says that I have them in the wrong order.
Yeah, mine's the same.
Really?
Yeah.
Hmm. You know what? Okay. Yeah, let me fix that afterwards then. I'll fix that. Okay. So good deal. From the bottom function to the top function, 1/2 x to square root of x, and then I have f of x, y. I wonder what was the biggest mistake. I'm probably just copying it wrong off of there, I guess. F of x, y, dx dy, and there it is. All right. So that was number 3. So aren't you glad we went over this? All right. So,
Would it be dy dx for that one? since you're-
yeah, dy dx. I'm looking at copying again Yeah, so dy on the inside, since you're going between y equals x and y. Okay, good. That's number 3. Number 4. That we want to make sure we do is Lagrange multipliers. This is a constrained optimization problem. Find the maximum min subject to a constraint. So we want to maximize and minimize. I have to put a short version of this, so it's been too long. The function f of x, y equals x minus y, subject to constraint that x squared plus y squared equals 16. Well, what you want to do in all these is always rewrite this as f of x, y equals 0. So you rewrite this as x squared plus y squared minus 16 equals 0 is one way. And then once you do that, you can call this g of x, y. That's the constraint equation, g of x, y equals 0. This works just as well because g of x, y equals a constant. We never see that. So, now the Lagrange multipliers. Lagrange says if it has a constraint maximum and it occurs at a point where gradient of f is a multiple of lambda, we call the Lagrange multiplier times the gradient of g. Well, the gradient of f, right, partial with respect to x is 1. That multiplies I. Plus partial with respect to y is minus 1. That multiplies j. And there is df dx times I plus df dy times j gives you the gradient of f. That has to multiply lambda times the gradient of g. Partial of g with respect to x is 2x. That has to multiply I. So the gradient is the vector of partial derivatives. There's this first component. Set the partial with respect to y is 0 plus 2y plus 0, so it's 2y. Okay. There's the Lagrange multiplier equations. Well, for vectors to be equal, these components have to be equal. So this is equivalent to 2 equations. One equals 2x lambda. These equal. And this one, minus 1 equals 2y lambda. And there's lots of ways to solve these. One way to do this, as I solve this for x, I wrote x equals 1 over 2 lambda. You didn't have to do it this way. I got y equals minus 1 over 2 lambda, which implies that y equals minus x, among other things, right? Then this isn't sufficient. Normally, you also need to put in the constraint x squared plus y squared equals 16. So you can plug this in. You can plug lambda in for both of these and find lambda. That was fine. But since you happen to be lucky and know that y equals minus x, you can take the constraint. I'll write it in the original form, x squared plus y squared equals 16. And I'll plug in y equals minus x and get even easier. Get x squared plus minus x squared equals 16. That says 2x squared equals 16 or x squared equals 8. X equals plus or minus 2 square root 2. So all the points, the only points we have to check are x is plus or minus square root 2 and y is minus x. So there's only 2 points to check, which tells you immediately one of them's going to give you a min and one of them's going to give you a max. Since we know for this constraint problem, there's going to be a min and max. Sometimes there's not. It depends on the problem, right? How do we know there's going to be a maximum and minimum on this one? It's because we're picturing this in our mind, saying in x, y, z space, we have this f of x, y equals x minus y. That's a plane, right? Z equals ax plus by is a plane. So it's some sort of plane sitting up there. That's probably not what it looks like. But we don't need to know the exact picture. It's just a plane, not a horizontal plane or a vertical plane or anything. And it's over, and we're subject to the constraint that x squared plus y squared equals 16. That's a circle of radius 4 in the xy plane. So subject to that, we move around a circle, x squared plus y squared equals 4, the xy plane. Where's the maximum value? Well, we know it's going to occur because this is a continuous curve and a continuous surface. We know it's going to there's going to be a maximum, this is for continuous regions. Somewhere there's going to be a minimum somewhere, right? And if you really think about what we're gonna get up here, you would project a circle up onto a tilted plane as an ellipse. So there's gonna be a maximum point on the ellipse, a minimum point on the ellipse, and within the plane here. And that's what we're finding. We're finding that one of these points is the highest point on the plane over the circle, and the other one's the lowest point on the plane over the circle. The 2 points we get are 2 square root 2 and minus 2 square root 2. And minus 2 square root 2 plus 2 square root 2. So you just plug those in and see which is the larger, must be the max, smaller must be the minimum. And this one turned out to be the maximum. Yield the maximum. It gives z f of x, y. Equals 4 square root 2. And this point, back, gives the minimum. F at minus 2 square root 2 plus 2 square root 2 came out to be minus 4 square root 2. So there was the maximum, there was the minimum, and these are the points they occurred at. All right. Let's look at 5. Then the volume of the solid bounded by z equals x plus 2 above, z equals 0 below, and within the cylinder x squared plus y squared equals 1. Find the volume of this. So again, on these volume problems, it's usually best to sketch it. So it's inside the cylinder. X squared plus y squared equals 1, the unit radius cylinder. So you just draw in the xy plane the circle x squared plus y squared equals 1. And you extrude it vertically, right? Because z can be arbitrary then. And it's this cylinder like that, right? There's the cylinder. And then we say above, bounded below by z equals 0. Well, that's just this bottom plane here, the xy plane. And above by z equals x plus 2. So it's a plane that comes down through like this. Again, if it's ax plus by equals plus cz equals d, then it's a plane. So this is a plane. And so what we're doing is we're going to cut this in an ellipse up here. And so it'll have an elliptical top and a circular base. And we're saying, what's the volume of this sort of prism or something? Where it looks like that. Right? This is the top surface. This is the bottom surface. And the sides of the cylinder. Well, what you want to do is take the volume equals the integral over the plane region here. If I call this R, the double integral over R of the height of the top surface, f of x, y, dA. And that's how we define the volume for a surface that's non-negative like this one. I think it may come down and touch here, I'm not sure, but it's not negative anyway. Now, how do we evaluate this to do a double integral over the region? We could do it in polar coordinates since it's a circle would be nice. So we can let R go from 0 to 1, right? And theta go from 0 to 2 pi. We'll sweep out the circle. The unit disk, I guess I should say, because it's the circle in its interior. And then f of x, y is the height of the top, which we said the top had equation z equals x plus 2. I should have written z equals x plus 2. And so that needs to be put in polar coordinates. It's r cosine theta. So we'll write for f of x, y. You can think of this as f of r cosine theta, or sine theta when you switch to polar coordinates. So you just replace x with r cosine theta. And then dA in polar coordinates becomes r d theta. Recall. Otherwise it doesn't. Right? area element. And you evaluate this integral then. With, you want to do this one or can I just write the answer? Maybe?
I'm okay with just the answer, but if you guys want to hear it, then.
Okay, well, we can look at it then. Let's see. I got this is then the integral from 0 to 2 pi. If you integrate here, r squared cosine theta, you get r cubed over 3 cosine theta, doing a partial integral, treating theta constant. And then integral of 2r gives you r squared. And then you evaluate that, and r equals 0 and 1, and integrate with respect to theta.
I see what I did wrong there.
Okay, now, this is just a calculus. Well, first put in what r is, so this is the integral from 0 to 2 pi. We put in 1 and we get 1/3 cosine theta plus 1 d theta. This is a calculus 1 integral, so we evaluate it, comes out to be 2 pi. And finally, number 6, I slipped a minus sign. This would have been a more interesting problem, except I put a plus instead of a minus. Find the local min and max, or relative min and max, which I say relative, same thing. But let's find the relative min and max of function f of x y equals x squared y plus 9y. On these problems, you set the partial derivatives equal to 0 to find the critical points, and you check each one with the second derivative test, right? Which also finds saddle points. I asked for on here, forgot to write down. But you set df dx equal to 0. Well, let's see, that's 2xy. Well, this means that either x equals 0 or y equals 0. So in the xy plane, to find your critical points, your restrictions be on one of the axes already, right? And then you set 0 equal df dy. And let's say that's x squared plus 9. And this can never equal to 0, right? X squared, a non-negative number, plus 9 is impossible. It's impossible to make equal to 0. There's no critical points. So there's no maximum, no minimum, no relative maximum, no relative minimum, no saddle points either.
Stared at that one for the longest time.
Oh, yeah, well, see, because you couldn't believe it was that easy, right?
Oh,
If it had it been minus here, it would have been more interesting. Then it's x squared minus 9 equals 0, and x equals plus or minus 3. And then y has to be equal to 0 to satisfy this one, so you get these 2 points. 3, 0, minus 3, 0, and you can apply your second derivative test to those two. So next time I'll final or something, I'll get it right. Anyway, so on this one, there were no critical points. So no maximum and minimum.
I didn't even think that would even be the answer.
Yeah,
I thought it had a number solution.
yeah,
Me too, I was just like, okay, well.
that's why I wrote it. That's too easy. All right. Okay. That's it. Any comments online? All right, well, let me know as you have more questions. We can answer some more questions after the class, for instance. Today, I'm going to skip over a section. I think it's probably the hardest analysis of the semester. It's not like it's the most important material, it's less important material. We have to do it, it's somewhat important. I'm gonna skip over 14.5, I'm gonna move on to 14.6, which is not as hard, and then we'll come back to it. Or my sections, right, let me make sure. Oh, I'm sorry, we're skipping over 14.4, and we're going to 14.5, which it sort of comes naturally first anyway. I don't know why they put them in this order. Maybe there's some reason I haven't figured out, but 14.5 which is in, triple integrals. We've been doing double integrals, why can't we do triple integrals? And so we'll say this, suppose we have a function f of x, y, z of 3 variables. We can do something analogous to what we do with functions of 2 variables, right? We did calculus functions of 1 variable and calculus 1. We just recently did functions of 2 variables, like finding max and min and these kinds of things. What if we want to maximize and minimize a function of 3 variables? What we can do, or find volumes with over a region 3 space, so we get 4-dimensional volumes. Given one of these, the triple integral over a solid, I'm trying to remember what letter they use now. I think they, 2 books, one used W, this one's used G. Over a solid G. With its closed and bounded. Three dimensions. So closed means it includes its boundary. Bounded means it doesn't go out to infinity anywhere. It is found in real nice analogy to what we did for functions of 2 variables, so we'll sort of solidify what we did there. So we'll make an analogy to the double integral over a plane region R of a function of 2 variables. But it's now written. You have to be careful in mathematics, calculus books. This is ubiquitous. Every calculus book writes it like this: triple integral over the solid. They often use different letters for the solid, but other than that, it looks the same. F of x, y, z dv. And the idea is this is over an area of a plane region R, and this is over a volume of a solid G. So in this case, what we did was we said we had a picture, and suppose we had, well, let's just put the region R for now. If I have a plane region R that's closed and bounded, how did I find the double integral of a function over that region? What I did was I found any enclosing rectangle whatsoever. Since this is bounded, I can enclose it in a rectangle, and then I partitioned it. Remember this? And I started this as x0, x1, dot, 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 xm. And I partitioned the y-axis, y0, y1, dot, 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 up to yn. Good. Break this up into little subrectangles, and each subrectangle, A, J, K. If I call it delta A, J, K, meaning the little area of delta of A, J, K, is the width here, delta xj, times the length here, delta yk. And we said, what does the double integral mean? When you write this notation, double integral f of x, y, dA, it meant the limit if you let capital N, let's say, equal m times n, since there's mn rectangles in here. Limit as capital N goes to infinity with both little n and little m going to infinity, so the smallest width and length both go to 0. So the width and the length that are smallest both going to 0 in the process of the sum J going from 1 to M, K going from 1 to N, F of xj star, yk star, any point in the JK rectangle here, so you just take whatever point you want, xj star, yk star for the JK rectangle. Multiply that times delta xj, the jth width, length, times delta yk, the kth height. And that's how we define this to be, or what we define this to be. And it doesn't make sense if you can get different numbers, which said if this exists regardless of the choice of partitions in both directions, regardless of the points you pick inside each region, then we say this is the definite integral exists. And it turned out that if f is continuous, and for nice boundaries like type 1 or type 2 regions, or more generally, a piecewise smooth, simple closed curve, more generally you can do this for, but then it's harder to evaluate these. You always get the same answer regardless of the partition or the point you choose. So we say because it's the same answer, it must be significant. We define that to be the double integral. And that's what we said. Now we can do the same for triple integrals. If we have in 3 space a solid Easter egg or something, G, we can say if it's closed and bounded, then we can find a rectangular box that encloses it. And we can partition the box in X, Y, and Z. So we partition it this way with the delta xj for the jth width. We partition it this way with delta zk there delta zl for the Lth height. And then in y direction, we also partition it. This is, oops, that was y. This is delta yk. Sorry, this is the y-axis, so I'm partitioning a y in this direction. So here's y, x, z, the standard configuration. Delta yk is the kth width, and then we take over here delta xj. So delta xj, delta yk, delta zk gives the volume of the JKL box that's in here. Because it's the length, width, and height of that. And we say delta V JKL XJ delta YK delta ZL. And the triple integral, defined in analogy to this, we'll say that the triple integral, when we write this notation of the function of x, y, z that we're given, dv is equal to the limit as n goes to infinity, where n is the product of these. There's if there's m of these, maybe this is xm at this position out here. We go from x0 to xm, and then y goes from some y0 to yn at the end, and z goes from whatever z0 is its initial height up to the top point here, which is z p or something. Then this is limit n goes to infinity, the sum L going from 1 to p, sum k going from 1 to n, sum j going 1 to m of f at any interior point to this box. So somewhere in this box, we put a point xj star. We can take any point we want, yk star, L star. And you pick that arbitrarily. And then, multiply by delta xj, the width of the jth increment x, delta yk, the length of the kth increment y, delta zp. And that becomes by definition the definite integral here. And if this has the same value regardless of the partitions with all the widths, lengths, and heights going to zero as n goes to infinity, regardless also of the points you pick within each box, then we say that definite integral exists. And it turns out if f is continuous, we'll write that down. If f is a continuous function of 3 variables on R, and G is a nice solid, I better continue it up here. Word nice isn't well defined in mathematics. The thing is, you can make pretty complicated solids for which this works. So we'll just say, and G is a nice solid with quotation marks, such as the most important case is if it has a top surface Z equals, or like bottom surface Z equals F1 of XY, Z equals F2 of XY, are continuous functions giving the bottom and the top of the surface respectively. So on the picture here, what we can do is break our Easter egg here into pieces. There's a top surface up here, which is F2 of XY. And there's a bottom surface, F1 of XY. And so this one is just, Z is a function of XY, gives the bottom surface, Z is a function of XY, gives the top surface. If those are continuous, and now you see why this can be quite complicated. And over a region R of projection below in the XY plane, that is one of them we've already done, say type 1 or type 2. From when we did double integrals. So that's one special case, but you make more exotic cases than this. This is the one that's of interest because it comes up in most science problems. You have a case like this. But the idea is, maybe I better draw a picture here. A new picture, unless I clutter that too much. You have some solid G. It has a top surface. G equals F2 of XY. That's a continuous function. It has a surface on bottom, Z equals F1 of XY, which is continuous. And if you think of shining a light vertically down here so that it makes a shadow down in the XY plane, the shadow is in type 1 or a type 2 region. In other words, it's got a two continuous curves on the boundary and goes between X equals A and X equals B, or Y equals C and Y equals D. So type 1, X would go between A and B, and you'd have a curve here that's continuous. Y equals whatever, G1 of X, continuous, which is the bottom curve if you look at the XY plane. And a top curve in the XY plane, Y equals G2 of X, which is continuous. So that's the common case, is you have this region R, that's the projection of this line shining straight down, gives a nice type 1 or type 2 region, and the solid itself has continuous top and bottom surfaces. Then for a continuous integram, this exists with the same value regardless of how you box it in and all that sort of thing. And so so this is real nice for exactly the kind of problems we want to be able to deal with. It always has a unique answer, and we call that the value of the triple integral. Now, just as when we did functions of two variables, if you don't draw this again, but remember when we did a function of two variables, we had some plane region, and we integrated the double integral over R of f of x, y. The a and f was non-negative, so we're taking, there's some z equals f of x, y. This is our double integrals. What did we get when we evaluated this double integral for a continuous surface up here that was non-negative? We took this double integral. Remember we got the volume below the surface? So we defined that actually be the volume below the surface. We could do that. It was adding up the height f times the little area of the rectangle down here. That gave us the volume below the surface. Similarly here, what we're doing is we can interpret this if you want as a four-dimensional volume. There's a fourth dimension that we can't picture on the board because it's too hard. But the idea is exactly the same way. If it has a fourth dimension, then it can be the, between three-dimensional space and this solid and another in the solid top surface, the volume in four dimensions. That seems kind of abstract, and who would ever need to do this? So why would this possibly be useful if we're not interested very much in four-dimensional volumes? Here's where it comes into play in a lot of the sciences. So let's make this the following note. Despite that maybe the geometry is unusual, except for mathematicians who like to be abstract, this triple integral over a solid f of x, y, z, with f of x, y, z equals some sort of a density. It could be a mass density, or it could be a charge density, or something like that. It has a value, because not only could we interpret this one, if we integrate over a plane region, a function f of x, y, we can think of it as a volume. We could also think of this f of x, y as maybe the density of this lamina, this flat plate, that we want to maybe find the mass of it. If this is the density in maybe kilograms per square meter, and we integrate the density over this thing, we could get the mass. Or if we integrated the charge density, we could get the charge, right? Similarly here, this one will give us the mass of the solid, G. If f of x, y is the density of G, and the integral exists such as f of x, y, z is continuous, which so there's the application, is that you can calculate mass or charge or some other thing that's enclosed within there. It could be more abstract too. I mean, F could be the density of houses, and you integrate over a three-dimensional region, get the density of population, and get the population within the volume or something like that. So it can be a density of anything. It doesn't have to be mass or charge. So that's where it comes from. You want to have this concept that just like you enclose the region inside little rectangles, we can enclose a volume inside little rectangular parallel pipettes, little boxes. And when we integrate over all the boxes, a function, we can think of that as giving the mass of the solid G. All right, so that's all the theory behind it. There's some theorems that come up now, which is what you're probably more interested in for the homework, right? Theorem 1 is also named after Fubini because it's essentially the same thing with one more dimension. And it says this: if R is a rectangular box. Set of all x, y, z, such that x goes between A and B. Y goes between C and D. I think the book used between K and L for Z. Could have been P and Q, it's one of the, Z goes between K and L. So it's a rectangular box. And F is continuous on the region, I don't care what it does outside. Then the value of this triple integral, which could be quite, who wants to do the limit of a triple sum like that, right? It's just terrible to try and evaluate it from the definition. But Fubini says, by magic again, that you can evaluate it as an iterated integral, just like for double integrals, you did an iterated integral, where z goes from f1 of xy, the bottom surface, to f2 of xy, the top. I'm not writing this right. K to L, z goes from K to L, y goes from C to D, and x goes from A to B, runs over the box, f of x, y, z, dz, dy, dx. You can do 3 calculus 1 integrals, except that just like with the iterated integrals for double integrals, each inside integral is a partial integral. So this is a partial integral. And on the innermost integral, you hold both the other variables constant. So you treat x and y both as constants when you do this integration. Right? And then on the next integration, z is gone because you just integrated over z. And so on the next integral on the inside, it's a partial integral holding the one remaining variable, x, constant. So that's what you do. We call that formula 1. If it happens to be a rectangular box you're integrating over, how often do you get a rectangular box? Well, in practice, right, a lot of people make rectangular boxes for the sciences, so sometimes you do. Even so, this is important because it helps to lead into the next theorem. That'll be equation 1. For Fubini's theorem, you just go A to B, C to D, K to L, partial integrals on the inside, right? Then you can evaluate the triple integral. With a little more work, you can establish another more general theorem. For what I called an example of a nice solid, because it always works for these kinds of solids. Oh, and by the way, I forgot to write something else down here. There's nothing sacred about this order. You can integrate in any order. There's actually 6 different orders when you have 3 different variables, right? Because there's 6 different permutations of x, y, z. Ever seen that in combinatorics or probability or something? There's 6 different orders you can arrange them in. It's when there's n objects, you can arrange them in n factorial ways. So there's 3 of us, 3 times 2 times 1, 3 factorial equals 3 times 2 times 1. There's 6 different ways you can. Right, you put x first, x, y, z, then you can interchange y and z, then you can put y first and interchange x and z, and then put z first, interchange x and y. 3 different letters you can put first, and then 2 different ways for each is 6. So we'll say and 5 other orders. You can integrate into any order and it gives you the same value that we call the triple integral, according to that definition. Now, more generally, for a simple XY solid, which is exactly the kind I mentioned before, that means Z equals f2 of xy, continuous function is the top. Z equals f1 of xy, continuous function is the bottom surface. Bounding the solid. And then the projection R of the solid is type 1 or type 2, meaning continuous boundaries and one variable goes between constants, the outside variable. Type 1 or 2. For these kinds of regions and some others, but these are the ones that are important. The triple integral of a function of three variables provided the integrand is continuous or some other what, you can have a finite number of bad spots in here, for instance. F of x, y, z, the integrand also continuous, can be evaluated by integrating the double integral over the plane region of projection R of the integral from the bottom surface f1 of xy to the top surface f2 of xy. The integrand f of x, y, z, dz, dA. What does this do for you? This will be formula 2. So there's two different new, and this is triple integral over the solid G. I'm going to run my G on there. I don't know why they picked G. It's always nice to, R region, right? I think S solid, but nobody uses S. The other book I like uses W. I don't know, anyway. But we'll call that formula 2 then. That's the second theorem. You can use either one of these. That one's only for the special case of a rectangular box. This one is only for the special case of the simple XY solid having this description. You can evaluate it. But what this does for you, I started to ask, is you evaluate this inside integral, treating x and y as a constant. And then you have a double integral. You go back to your double integral techniques, and it's over a plane region R for which the double integral is nice, right? So that's the idea: is you reduce it one dimension, then you use your double integral technique. This one you just do the iterated integral straight. This one you get a double integral and use your previous results. Either way, you have something you can do now. But if I haven't used up too much time and have time for an example, I guess figure out what I can do now. I didn't think this was so long to present the theory. Let me give you the homework here so I don't forget also. 14.5, this is what I'm going to ask you to do. These are not real long problems, but longer, so I don't have a lot. 7, 11, 17, 21, and 25. If you have trouble on any of those, look at some of the other odds, and they'll also have answers in the back. I tried to pick ones that brought out the concepts without being too trivial. So I didn't, I could have picked 1 on here, but I thought 1 was kind of trivial. And 7 brings out the details more. So if you have trouble with 7, try 1 first and then go on to 7. I don't think you need to do 1. But here's an example. Well, we should do a simple one first. Evaluate a triple integral. Let's do this one. X, Y, Z, dV over a solid G. Where G is the solid bounded by the parabolic cylinder. You can see this gets pretty tricky. Yeah. It really helps to draw these in a big hint. By the parabolic cylinder, y equals 1 minus x squared. Wait a minute, isn't that a parabola? How is a parabolic cylinder? It's in 3D, right? Z is arbitrary, so you extrude the parabola y equals 1 minus x squared into a parabolic cylinder like this. Here's the xy plane. You draw the curve y equals 1 minus x squared, right? How do you draw y equals 1 minus x squared? XY plane. Y equals x squared is this basic curve, right? Y equals minus x squared is the basic curve upside down. Y equals 1 minus x squared takes this one and moves it up 1 unit. So it looks like that. It goes through 1. It's the baby parabola y equals x squared. Turned upside down and slid up 1 unit. That's what this is. So it looks like this in the xy plane here. Goes out to y equals 1 and heads back that way. And that's the parabola in the xy plane. Then z is arbitrary, so you draw it like that. Tricky drawing in 3D. You gotta learn techniques, I guess. But there it is. This is the parabolic cylinder y equals 1. All right, so that's one boundary. I don't want to give you the trivial ones. Anyway, oops, except it's 2 minus x squared. How did I copy that wrong? Oh, I copied number 10 there. 2 minus x squared. So that this is, just to make sure I don't give hard numbers in here, let me switch this. This goes up to 2. I just slipped it up 2 units. So this is y equals 2 minus x squared. I just need to shift it up 1 more unit. All right. And the planes, 3 planes, do them pretty easy. Y equals 0, z equals 0. 2 coordinate planes. And the plane y equals x. So y equals 0 is the xz plane right here. Here's y equals 0. So this parabolic cylinder, I'm going to cut it off right here, like that. That's, so it looks like it stops here at the plane. So that's the back surface, is the z y equals 0 plane. And then the z equals 0 plane is this xy thing here. This is z equals 0. This one, y equals 0. And then y equals x. Oh gosh, that's what it does. I'm copying this down wrong. All right, must be getting late. So I'm starting, keep going back and forth. I'm looking at number 10 and then number 11 and copying the wrong one. But it was z equals 2 minus x squared in these 3 planes. Otherwise, I have to change it. I have to change one or the other. Let's do that one. And in the xz plane, you take the baby parabola z equals x squared. Turn it upside down. Here's z equals minus x squared. Shift it up 2 units in there. Z equals 2 minus x squared. Oh, all right. And now that one in the xz plane, here it is, looks like this. And you extrude it because y is arbitrary, so it looks like this. There's the cylinder. Z equals 2. Now you use the plane y equals 0, which is this one back here. XD plane. Z equals 0, which is this one down here. The xy plane, and y equals x. which, if you put y equals x in the xy plane, it splits the axes. It's this line right here in the xy plane, y equals x. And I extrude it upwards and I come up with to the cylinder like that. So this is the one boundary here. And now you can sort of see it. It's here. It's between this plane, and this plane, and below this parabolic cylinder. So it's kind of hard to draw, but there's our volume G in the back plane, the bottom plane, and this angle plane going between the x and y axes vertically in this mailbox kind of shape. All right, that's the solid G that we want to find the volume formula, the integral for. So let's try that. The volume, again, has this following note. Just like if you took the double integral of 1, you got the area of the plane region. If you take the triple integral of 1, dV over G, you get the volume of G. So I just put integrand 1 to calculate a volume. So I'll say this is the triple integral, right? Because this is just adding up in that Riemann sum. So we had the triple sum. Delta x times delta y times delta z. This is adding up the limit of the sum of the box volumes, the little box volumes. So will give us the volume of the solid. So we'll take the triple integral of G is the double integral over R by formula 2 of going between the bottom surface and the top surface. So you look at it and you say, what is the bottom surface and the top surface? The bottom surface, if you look at the solid, is the plane z equals 0. So I'm going to start at z equals 0. This is the bottom surface on the inside. That's this one. F1. And the top surface is the parabolic cylinder, z equals 2 minus x squared. So the top value is 2 minus x squared. And then then I have the integrand x, y, z. I'm sorry, not 1. So I started to copy that off the other problem too, didn't I? They wanted me to integrate x, y, z. We'll just say find the volume. I said evaluate this, didn't I? All right, so we'll evaluate this. Sorry. So I'll do triple integral of x, y, z. It's no longer a volume, it's the mass of the solid. If this is the density point x, y, z is x times y from z. And we put dz here and dA here. So to evaluate this triple integral, maybe the mass whose density is x, y, z. By formula 2 here has this triple integral. So now how do I evaluate that triple integral? What you now do is you go look at in the xy plane of projection, this region down here is R, the region of projection, right? This is why you draw it. You say the solid projects onto this region down here. What is that? Well, that's something in the xy plane with this line here, y equals x on one boundary. And this line right here, what is this line equation? Well, it's where you intersect along the x-axis here. If you have z equals 2 minus x squared, to find where z is equal to 0, you put 0 equals 2 minus x squared, and you get x equals plus or minus the square root of 2. That's where these 2 points are, minus square root of 2 and plus square root of 2. This is therefore the line here, this intersects at plus square root 2 here, minus square root 2 over here. And we want the one that's plus square root 2 because it's in the first octet up here. So we'll go to x equals plus square root 2. Bounded by this line, x equals square root 2 in the xy plane. This line here, y equals x in the xy plane. And the line here, y equals 0. Y equals 0, x equals square root 2, and y equals x gives the triangular region R, that's the projection of a solid. So The theorem says you take the double integral over the region of projection of the solid of the single integral, bottom surface to top surface, integrand, whatever it is, dz dA. Now you can reduce it because the integrate over R, you go back to your, suppose I call this a type 1 region with this the bottom curve and this the top curve, x going between 0 and square root 2. So I'm going to just put the double integral for R as x going from 0 to square root 2. From the bottom curve, y equals 0 to the top curve, y equals x, means I go from 0 to x. Then I go from 0 to 2 minus x squared, x, y, z, dz, dy, dx. Here's, I'm out of time here. So I'll say, there it is. Now we have to, maybe I can do one more thing here. Because this integral is a product, you can't do this in general, but because y and z are held constant, I can take these out. I can put y into the y integral and x into the x integral if I want, make it a little easier. But you do this now with the inside integral holding x and y both constant. And I integrate z and I get xy times z squared over 2. Plug in z equals 0 and 2 minus x squared. Then I'll have to do the double integral of that over y and x. So maybe I'll leave that there, but time. Try these homework problems and we'll do some more of these next time because I didn't finish. Thank you. Have a good evening. I'll look for the key online. If you didn't get your test back online, then see if I can send it to you soon, or you can come pick it up.
Here you go, Georgia. Thank you. Yeah.